go into that today. Today, I wanted to just highlight an instrument that's been being built in the lab to look at these two technologies as a rapid way to screen the bilayers for different conditions as we optimize our bilayers for the more sophisticated structural measurements. So the electrical impedance spectroscopy of the tethered bilayer simply is working as a function of the fact that the lipid creates a fairly highly insulated system between the solvent and the gold surface here. So you've got a resistance of the membrane and a capacitance of the membrane, and both of those electrical properties are highly sensitive to the integrity of that membrane. If there are defects in that membrane, or if there's any holes that are in the membrane, this ion flow will detect it. So, and what the data looks like is essentially, it's not really important exactly the presentation, but what you're measuring is basically an impedance as a function of frequency in the measurement. And these are typically plotted out, so this is simply impedance versus frequency for different preparations of the membrane. And these are typically plotted in a two-dimensional plot of the real and imaginary component of the impedance. And you get these sort of upside-down curve type structures in this cold plot. And again, the important thing for this talk is to show that when you have a bilayer formation, the impedance response in this curve is very dramatic. So this green curve represents the surface before the bilayer, and the blue little curve down here, which is blown up, represents the impedance profile that one expects for a highly insulated bilayer formation of just the bilayer. So the response of these curves, the movement of this curve in